When we built our transform for 360 video, we had to solve a lot of engineering problems. The first was to address the drawbacks of an equirectangular layout. Imagine a 2D map of the globe. Antarctica, which is actually a circular landmass, appears linear and stretched out. How you display the map affects how Antarctica appears in the image. The same warping effect happens in 360 video, as you can see here at the top and bottom of the image. This happens when pixels are stretched when the video is rendered, resulting in redundant information. We solve this by using a technique called cube mapping. A cube map projection is a combination of 6 faces of a cube. Each face represents one direction relative to the viewer: up, down, left, right, front, and back. This technique is commonly used in computer graphics, often to represent images with a practically infinite distance away from the viewer. So, how did we make it work in 360 video, where the perspective is controlled by the viewer and constantly changing? We start by splitting the frame into 6 areas that represent each of the viewing directions. We then map each section onto the corresponding cube face. The cube map contains the entire 360 video, but without the redundant information from the equirectangular layout that causes warping. This reduces the file size by 25%, which matters when operating at Facebook scale. Each face of the cube is treated equally, which preserves the video quality and resolution no matter which way the viewer is looking. Simply put, for each frame, we put a sphere inside of a cube, wrap an equirectangular image around the sphere, and expand the sphere until it fills the cube. This works great for watching 360 videos in your newsfeed on Facebook. But things get a little bit trickier in VR. The videos are higher resolution, at double the frame rate, and we don't want to wait for buffering. So this time, we decided to put a sphere inside of a pyramid. But now only one face, the base of the pyramid, is rendered in full resolution. This is the viewer's field of vision. The rest of the video gradually decreases in quality as it wraps around the viewer. We split the 360-degree sphere into 30 different viewports, separated by about 30 degrees. That way, as the viewer looks around, we can dynamically switch between viewports for optimal resolution. With pyramids, we can reduce file size by 80%. Now we are able to bring high-resolution 3D videos in virtual reality to you.